Hi class. Today's lecture is related to the principle of linear impulse and momentum and conservation of linear momentum for systems of particles. This section 15.2, unlike 15.1, it's dealing with multiple particles interacting with each other. So we will learn how to apply the linear impulse for a system of particles and also apply the conservation of linear momentum. Previously, in section 15.1, what we studied is the momentum diagram where we have a particle and this particle has an initial momentum L1 and that is equal to m1 v1 vector, and when this particle that has a mass m undergoes an impulse force netted by summation of all the impulse forces F dt vectors, it's going to lead to a change in the momentum of that particle to L2. Let's say this has a direction of this way, so we expect that to alter and change to L2, which is equal to m to v2. Now, we took some example of a ball bouncing off the ground, where the ground has been considered to be not moving, but in reality the interaction and impact happen with multiple particles. So section 15.2 talks about what happens if you have multiple particles. Each of these particles has their own identity, meaning they have their own linear momentum, m1 v1, let's say m2 v2, and let's say here m3 v3, and so on, mn vn, and they are interacting with each other, meaning multiplying. Some of them will multiply against each other, or they could be moving all together in an aggregate motion or in a lumped motion. So we'll study how to study the momentum for these multiple particles. The easiest way to look at this problem is first to study the interaction between two particles. So interaction or impact between two particles, which is the easiest way to understand. And then we'll generalize this to multiple. Say that I have a particle that is moving in certain direction, let's call it m1, and I have another particle, m2, and that is also moving in another direction, v1 and v2. Suppose these are moving in opposite direction, v1 and v2, and these are vectors. I know they're here for simplicity. We assume that the motion is rectilinear, meaning it's one dimension. So all we said, we establish the coordinate system. Since the motion here is only concerned with an x, so all of these are in x direction. Now we expect that the motion of m1 and the motion of m2 to change, right? So if I were to apply the principle of linear momentum, which is we discuss here, for particle 1, what we expect is from the momentum diagram is that before its motion plus the impact force that is happen at the moment of impact, which is at the impact plane, delta t, right? And I'm going to assume that there's an impact, so impact happening between 1 and 2, right? So just to signify that, for a period of time t1 to t2, is going to lead to a change in the momentum of the mass v1x. I'm going to put here a prime to show it's after. So this is not a derivative, this is a prime, mean after. For particle 2, that has a mass m2, we expect also the same, m2 v2x plus. Now, the force that is applied from 1 to 2 is the same as from m2 to 1, except that they have opposite direction. So I expect this to be in a negative f12, simply because I'm going to write it over here, because f12 is equal negative f21, meaning the impulse from 1 to 2 is the same as impulse from 2 to 1, because that's the impact between the two same bodies, and they have opposite direction. All of these are vectors, but here I don't have to put vector because it's only one dimensional, and this is just for illustration. So dt equal to m2 v2x prime. Now we have two equations, as you see here. So I haven't used any further information from yet. I'm just using the previous information from 15.1. Sum 1 and 2. What do you get? You're gonna get m1 v1x plus m2 v2x plus, when you sum these together, it's gonna be 0, because this is the same as that magnitude. So plus 0 equal to the m1 v1x prime plus m2 vx 2x prime. Alright, so it means the linear momentum, summation of linear momentum of the system before is the same as, because this is m I v I, so in general form is equal to, and this is I, equal to the summation of linear momentum after m I v I prime. So this equation, you call it the conservation of linear momentum simply because during this impact, this is the impact, no external forces were applied into the system at the moment of impact or during this transition from before and after, simply because this came to be 0, and the only forces generated is the impact or the impulse force, which are going to oppose each other and equal to 0. You can think of it as an internal force that doesn't have an effect on the Newton's law. Alright, so we can apply this as a vector for any system of particles. Alright, let's talk about the principle of linear impulse and momentum. Now, I know in section 15.1 we said that a particle has m mass and it has a velocity, this is linear, and due to the forces, impulse force from T1 to T2 is going to cause a change, which is, let's say, m1 v2, right? Now if we have multiple particles, and I'm using a Cartesian coordinate system, right? and I have m1, m2, and so on, mn. We examined previously that the internal forces, impulses due to internal forces will be zero. So only the external forces. Let's designate that each mass has an external force, F1, F2, or external force that causes an impulse, and Fn. So for one particle, the impulse will be m1 v1 before plus the impulse force, the net impulse forces. I don't want you to get confused. I know we're writing summation, but that's summation for the net. So this is, consider this F here to be the net, is equal to m1 v2 for that particle, right? For the same particle. After. Okay, and I'm gonna put here 1. So 1 here, so 1, 1, the subscript, 1, 1, 1, 1 refers to the particle number. The, between parentheses, 1 here mean before, and 2 mean after. So this is after. Now if I have multiple, that will be defining the principle of linear and impulse and momentum for system of particles that one showed over here. It will be simply summation of all the linear moments of these particles before plus summation of all the net impulses, again emphasis net impulses, Fi dt, equals summation of the linear momentum after, where I is the 1 to number n. This is number of particles, right? So that's the principle of linear impulse and momentum for a system of particles. Let's take this fourth example. We have two blocks. Block A is spring-loaded initially at unstretched position, has a spring constant of 10 kilonewton per meter, and we have the velocity of A block is 0 at this instant, and there's a block B moving toward the block A at a velocity of 15 meter per second. If the masses of MA and MB are known, 15 and 10 respectively, find the maximum compression of the spring. To summarize the problem, we have two blocks. Their formation is given. The velocity before impact for block A is 0 and stretch position K is 10. I assume that the coordinate system is x to the left, positive. We're only concerned with the analysis in the x direction. Nothing is happening off the plane. So all our calculation is going to be assuming that the motions are VA and VB represent VAX and VBX. So no need to add this subscript. And also, we want to find the maximum compression of the spring, which meaning the moment when A and B velocity is equal to 0. Now what is given to us also is that block A and block B couple together at impact. So given that block A and B couple together at the impact, meaning they move all at once as one unit at impact. So if I want to break down what's happening, I'm going to break it down into the moment of impact, and what's happening after the impact. Okay, so at the moment of impact, let's say this is the moment when these both A and B couples. So at this moment, we know that VA, VB, just before the impact, it does have the mass 10 kilogram and a velocity of 15. And because A and B will travel, so both of them will have the same velocity after the impact. So I'm going to call them, in fact, VB or just V velocity after the impact. So this is the same as velocity after the impact. So moment of impact, this is after the impact, both of them couples and become together. After the impact, they will compress the spring by amount of delta S. And at this moment, the velocity become 0, right? So for clarity, I'm going to call this V prime. And I'm going to call this is V double prime. Not derivative, it's just an indication what's happening after. And this is after the impact, complete compression. So what happened with complete compression, that this velocity becomes 0 because they are together. Maximum compression means that both of them, all the energy has been transmitted to the spring. Alright, so we're going to solve one by one. Looking at the first portion, applying the linear momentum for a system of particles. We have two particles, so summation of moment, linear moments, M, V, right, I, plus summation of all forces, external forces, dt, equal to summation of all linear moments after, right, after. One thing about this system is that there's no external forces applied onto the system at the impact or during the impact. Therefore, this all becomes 0 and the problem becomes conservative. So the linear momentum is conserved. So therefore, you can right away say, okay, there is no external forces. You can say these two items, the linear momentum summations before and after are equal. So to further simplify, I'm going to write, so what we have the MA VA before the impact plus MB VB before the impact, and this is all in linear, equal to MA V after the impact, because both of them move at the same velocity, so both of them gain the same parameters, V prime, right? MA, and this is all directional, MA is 15, MA before is 0, because it's not moving, plus MB is 10, VB is 15, and the reason why is plus, because I assumed here is positive, equal V can come outside, so which is the unknown, MA plus MB, so it is 15 plus 10, right? So therefore, this is 0, V prime is equal to 150 over 25, and that's 6 meters per second, and it's in that direction. So we got the V prime at the moment of impact. Just after the impact. Now this energy will move the two masses at the velocity of 6 meters per second and compress the spring. Now we can apply the principle of energy, or the conservation of energy, because no losses are assumed. Therefore, the energy is conserved. It's just going to transmit from kinetic energy into a potential energy stored in the spring. So at the impact, okay, so kinetic energy plus spring energy, potential energy, this is just after the impact. Impact is equal to the summation of total energy complete compression of the spring. Now the spring is just after the impact is uncompressed, right? So therefore, this is 0. The kinetic energy at complete compression, the velocity total is 0, so this is 0. So what we're going to be left with is the kinetic energy of the system, because they are moving together, so they have a total mass, with their velocity just after the impact squared is equal to the complete energy due to the spring, which is half k, and this is delta S squared, right? Now half 10 plus 15, or 15 plus 10, V1 or V prime, which was 6, so this is 6 square equal half 10 kilo, so this is 1, 2, 3 delta S squared. And that is, so delta S, which is the max one, you just take square root, this would be 0.3 meter. So that's the solution. Let's take another example of 2 rail cars with masses of 20 megagram, which is 20 kilo, or 20,000 kilogram, and 15,000 kilogram, with velocity shown in the graph. We want to find the speed of the car A after the collision if the cars collide and rebound such that B moves to the right with a speed of 2 meters per second, and also find the average impulse force between the car if the collision place is during 0.5 seconds. So simply this problem, if you look into it, there's no external forces, so the conservation of linear momentum can be applied to calculate the speed of the rebounded car. Now, since we have already information about the speed of the rail car B, we can simply apply the conservation of linear momentum and calculate the velocity of car A. And we have to be careful with direction. So if we assume that the x direction is to the right, then 3 meters per second, or the speed of the car A is 3 meters per second and positive, while the speed of the car B is negative 1.5. And also the speed of the rebounded car B, which is going to move to the right, which is again in positive direction, so it's going to be plus 2 meters per second. Now the second part of the problem is asking us to find the average impulse force. Now we know that the two cars, when they collide, there is an internal impulse force that is acting on each car. They are equal in magnitude for each car and opposite in direction. So to solve for the impulse force, we need to take the free body diagram or the momentum diagram of only one car, because it's going to appear on that. So I'm going to use the presentation to go over the answer since we discussed that. So we apply the conservation of linear momentum assuming right is positive. So what we have here is summation of all linear momentum before, and this is after. Before, car A is moving to the right positive and has that much of mass in kilogram, and also this is how much it is for the car B with a velocity of negative 1.5 because it's going to the left. Together, when you sum them, is equal to the linear momentum summation after the impact. For the car A, which we don't know how much or where it rebounded, to which direction, but we know for the car B that is rebounded to the right with 2 meters per second as a positive. So we have one equation with one unknown. We'll find that the car A must be rebounded a positive 0.375, meaning it's going to rebound to the right and keep going to the right. That's what it means. So we expect this to carry on and keep carrying on to the right. All right. Now, as I mentioned, to find the impulse force, we need to get the moment diagram of only one car, because if you do it for the system, you're going to cancel each other. So we'll just take a look at one. And we apply the principle of linear or principle of impulse and linear momentum on the car A or B. So that's what we learned from section 15.1. You apply the principle, so the linear moment before plus the impulse force acting on it at the moment of impact equal to the linear momentum after for only car A. So for this is already calculated, you know it, and the impulse force, because this is a reactive force, force is coming from B to A, so it must be opposing the motion of A, so it must be to the left. That's why we have here a negative, and therefore putting together the numbers, you will find that definitely this integration of F delta T is equal to 52,500 Newton per second. Now, to calculate the F, we need to say, okay, how much is the average F force, assuming F average is a constant over the period of time 0.5 seconds. So this is similar of saying F average multiplied by delta T equal to that magnitude. So this is what happened here, which is assuming the average is a constant, and what it concerns us is that the integration and that rectangular area are equal. So therefore you solve for the F average and you will end up with F average equal to the impulse divided over the time, which is equal to 10 or 105 kilonewton. I'd like to close this class with a note and also with an example to do at home. The first note is the motion of the center of mass. For the system of particle that has a multiple particle, each is moving with a velocity or each has a linear momentum, we can describe the motion of the entire system as one unit that has a common velocity called Vg. And this is considered to be the aggregate velocity, which has a conserved linear momentum, which is described by Vg m total. That's equal to the summation of all linear momentum. So with that, it means that moving or dividing two sides by m total, you can calculate the aggregate velocity of that system by dividing the individual or summation of each individual linear momentum over the total mass. If you integrate both sides, then you can also find the position of vector that describe the motion of the center of the mass, right? Now the note that is related to the group problem solving, and I would like you to try it at home, is this example available on the slide. The problem here is require you to calculate the velocity of the crate and the velocity of the ramp when A reach B. So since these are two unknowns, you need to apply a couple of equations. One of them is the conservation of energy, because this system is supposedly here has no losses, and the second thing is the conservation of linear momentum, and also the relative motion between A and B, because A always slides over the ramp. So take a look at the solution and try it at home, and let me know if you have any questions. There is a lot of other problems you can try. It's all the same principle. Just by practice you will learn how to combine different equations from different laws.